I'm Jonathan Chambers, PhD candidate at UCL Energy Institute in my third year. I'm going to present my research thermal characterization of UK dwellings at scale using smart meter data. I'll breeze over this because I'm sure it needs no introduction. Energy in homes, important for climate, important for health. I think we're pretty much aware that there's targets, people dying, there's fuel poverty. It's quite bad, we need to fix it. So, for that we need to measure thermal performance in homes. We need it for all sorts of reasons. We want to track the state of the building stock overall. We want to track the state of individual dwellings, know what happens when you do renovations, if the renovations have been effective, if we're getting the performance we're expecting. We want it for regulatory compliance. You want various forms of certification when you install new measures. We are interested in things like performance-based contracting, that, for example, your contract states that if you don't get the performance improvements that you expect, or if you build a building and it doesn't meet what you required, then you don't have to pay. Now, at the moment, we mostly do these kinds of thermal performance measurements using the EPC, the Energy Performance Certificate, which itself is based on SAP, so the Standard Assessment Procedure. Now, this is a bottom-up method, involves a site visit. Usually for an existing building, you will use RDSAP, which introduces a set of assumptions, which allows you to look at a standing building, fill in basically a form with various bits of information, either ones you can measure on site or ones that you sort of assume based on a range of lookup tables. And from that you get an estimated energy demand, an estimated overall thermal performance of the building. And it's not very good on the whole. We find quite significant divergence between predicted and measured demand. Some people have called that as credibility gap. And I think that's important to think of it as credibility. Some people have also called it performance gap. Especially with SAP, that's a little bit misleading because SAP, in a sense, is never really designed to give you an as-built thermal performance. It's a sort of normalized system. But then people have started using it to predict real performance, and yeah, it's not really giving us the results we need. And on top of that, if you want to deliver these to every building, you have to send an inspector to every building. It's very slow, it's very expensive, it's quite intrusive. And as a result, you have energy performance certificates which are being delivered to buildings which are not terribly representative, which aren't being updated very often, and not really satisfying, I think, the demand for thermal performance measurement. So this is my research question: how can we do this? Basically the opposite of what I just said. How can we do it non-intrusively? How can we do it quickly? And how can we do it more reliably? What parameters can we use to characterize assessment? What data sources allow us to do this? And, well, can we determine a method which allows this to be done? And can that method be shown to be reasonably precise and accurate? And how does that then relate to what we already know? So my approach is what's known as data-driven grey box characterization. The little illustration gives you an idea of what grey box modeling is. If you have white box modeling, which might be something like Energy Plus, which is very data intensive, based on first principles, bottom-up building physics models, where you have a full understanding of the building physics going on. And at the other end, you have a black box model, which may be a purely empirical data-driven model. This is things like machine learning models, neural network models, and so on, where it's entirely data-driven, but you have very little understanding of what's actually going on internally. So a grey box model is effectively a hybrid model where you use the knowledge you have about building physics to create a partially completed model, and then you use data to finish it off. So you create a model with a set of unknowns based on the building physics that you understand, and from that, and from use some data to estimate the missing parameters. And we can do this because we have smart meters now. They're rolling out across the UK bit by bit. It should be in most homes by 2020. And with that we have total electricity and gas consumption, and we can also get weather data for the local weather data for a building, so that corresponds to that energy demand. And so we can use this to try and infer the relation between weather and energy demand based on unknown building physics. So for this I have a simplified physical demand model called an SPDM. Basically describe simple thermal processes as a kind of piecewise function. So we describe conductive losses, we describe radiative gains, wind-driven losses, gains from base loads, so gains from appliances. And then we define a set of link functions which effectively incorporate our assumptions about the relation between the thermal processes going on in the building and the final energy demand. And these are by necessity quite simple assumptions because we're trying to estimate some building physics with very, very little information about the building beyond its energy demand and its approximate location. But because we do have all these parameters explicit, or the assumptions are explicit, if we can get additional data, for example, if you have smart thermostat data, you can incorporate that into this model and refine the results. And this is where we get more into the methods. So deconstruct is what I'm calling the method, and it's an approach for estimating these parameters. So the problem is, once you have this model, you have a gray box model, and then you have a lot of data. Now, it could be tempting to simply try and fit all the parameters of your model to your data, just chugging it at a standard optimizer you might have from any statistical package. But there's a couple of problems with this. First, the energy data is very noisy. You know that there's quite a lot going on, and you also know that inside that noise there is a signal which is the physical response of the building. If you just try and throw all your data at your model in one go, you're probably not going to get very stable results. In fact, you don't. You tend to end up trying to manually fine-tune things for different data sets. It just doesn't work very well. And on a conceptual basis, it's also not very robust, because what we're actually doing here is saying, well, we know that inside the building energy data signal, there is some part which is related to energy data, energy demand that's driven by weather, and some part that's driven by something else, so probably behaviors or just things that we haven't really well described in our model. So actually what we want to do is find the parts of the energy data where we can best represent the physical processes that we're interested in characterizing. And this way we can basically take subsets of our data, and this is based on literature, I mean, way back to Bob Everett, we did similar work in the 80s, where you select subsets of data which best represent certain physical processes, and you use that to estimate the parameters in the part of that SPDM model that you're interested in. So the easiest example is if you say, well, we're interested in the conductive losses, the heat loss coefficient of the building. Let's just take a selection of data where we know that, for instance, there are very low solar gains, that there is a small amount of wind. So we know that probably we're not going to be observing wind-driven losses, we're not going to be observing significant solar gains. We can apply some heuristics to eliminate days where it's clear that the building is unoccupied. And from that we can get a subset of data which we think probably best represents the response of the building to change in temperature, and that is our heat loss coefficient. And that solves quite a lot of these problems when you just try to do this all at once estimation, which as you can see there, yes, conceptually less robust, as I said. You have potential biases. Again, another of our PhD students at the Energy Institute worked something similar and found that you can easily end up biasing one parameter with another, especially in terms of solar gains. You're very sensitive to outliers in your data. And just the fact that you have a lot of degrees of freedom in the model would mean that you could easily find locally optimal solutions for your parameters, and really fighting your optimizer is not something you want to do. So a little bit of overview. This is somewhat important, the data pipeline which makes all this possible. It's quite a significant amount of work. And it's actually my wish in presenting this to promote not just robust data pipelines, but also the sharing of robust data pipelines, which I don't think happens enough. So in my case, I'm using some SQL databases that stores considerable amounts of information, so energy time series data, site metadata, in a reasonably consistent format. I have a geographical information system, this PostGIS, which allows me to do location lookups, so that I can find the weather data, which itself is stored in gridded format, and I can basically do a fairly complicated join where I take site metadata. From that I can find the corresponding energy data. I can also find the average weather in that region. I can combine that together and I can feed that into my model. And so here's some preliminary results. These are a little bit old now, but I think for illustrative purposes they're quite interesting. And unfortunately, they never come quite right on the projector. But if you can see down on the left, this is energy data for the winter period overall, as a function of different weather parameters, as a function of external temperature, of solar radiance, and of wind speed. And that's really just to show that the data can be very noisy. You look at that and you don't really want to be fitting some kind of linear model into that. Now on the right you can see overlaid the subsets we take when we just take, this is always daily average data by the way, when we take data that we've selected to have a low amount of solar radiance, so we have low solar gains, and we've also removed unoccupied days, and you can see you have a much neater subset of data that's somewhat heteroscedastic, but still quite good. And we can apply this process to as many buildings as we want. The total buildings I have in my data set is approximately 15,000 at the moment, although there's no reason there couldn't be many more, and I am hoping to wrangle some more data sets eventually, but it's this for now. We can start doing bulk estimates. Again, I've got a little bit further than this, but this is basically to illustrate that the results are fairly sane. They give reasonable levels of errors. The process is quite robust. There's relatively few sites for which this really doesn't work. And that is part of my next steps, is actually to determine if we can find what properties of sites which fail this test, do they have something in common that we can say, when we take a much larger data set, for instance, we take the whole data set from an energy utility, can we tell which of those buildings are going to be, so to speak, well-behaved and which are not, and then you can start to give the well-behaved ones performance estimates. One difficulty is there's quite a shortage of data with which to perform any kind of verification. If we're estimating thermal loss coefficients, it can be quite difficult to find data that has any kind of thermal loss coefficient. The closest I'm able to do is that this method also can estimate mean internal temperature in the heating season. These things are actually measured. You can see at the bottom, this is outdated. I've actually improved it somewhat since then. But it gives you an idea of the difference between the estimated and measured average internal temperature for 25 sites. You can see for a lot of them we're within a couple of degrees, which, considering we know almost nothing about the sites, is actually quite good. This is not necessary. So yeah. So that's basically it. So, as I said, I've been trying to estimate the installation of homes, basically any home equipped with a smart meter. Since this will eventually be all homes, that could be quite a lot of them. It has to be scalable, and this is why we need this robust data processing pipeline, which makes it possible to apply not to a few hundred, but to thousands and millions of buildings. It's a gray box modeling approach. Yeah, the initial results are quite promising. There's a lot of work still, mostly to do with determining the levels of error and uncertainty, finding data sets to perform some kind of cross-validation, and ideally finding predictors of result quality, which means that if you can perform some fit, or you can observe something in the data that will tell you a priori whether or not your errors are going to be small or large, which means you can not only give an estimated performance of a building, but you can also decide whether that performance estimate is going to be any good. Finally, I'd like to acknowledge my supervisors, Taj and David Chipper, here at UCL, EDF Energy, who provide my studentship, and obviously PSRC too. Right, thanks.
Thank you.